Narration script. Inside Samsung's 120-inch micro-LED TV factory. How giant luxury screens are built, using 15 billion technology. Right now, somewhere in a building so clean that a single speck of dust could destroy millions of dollars worth of technology. A machine is placing objects smaller than a grain of sand onto a sheet of glass the size of a king bed. Each one of those invisible objects is a light source, and there are 24 million of them. Welcome to the most expensive television factory on Earth, where raw crystals become the ultimate display, a screen so advanced that fewer than 1,000 people in the world will ever own one. This is how a 120-inch micro-LED television is born. It begins not with electronics, not with plastic, not with metal, but with stone. Sapphire. The same mineral found in engagement rings and Swiss watches. But here, sapphire serves a radically different purpose. Grown in cylindrical furnaces at temperatures exceeding 2,000 degrees, these synthetic sapphire crystals are sliced into wafers, thinner than a credit card. They arrive at the factory sealed inside stainless steel containers, protected from contamination, the way a surgeon protects an open heart. Because at this scale, even a fingerprint is a catastrophe. The moment those containers are opened, everything changes. A technician wearing a full-body cleanroom suit, gloves, mask, hairnet, and safety glasses carefully breaks the seal. Inside, rows of sapphire wafers sit in custom foam slots, perfectly aligned, perfectly still. Each wafer will eventually become the foundation for millions of microscopic light-emitting diodes. But first, they must survive a gauntlet of processes so precise that the margin of error is measured not in millimeters, not in micrometers, but in nanometers. That is 1/1000th of a meter. For perspective, your fingernail grows roughly 1 nanometer per second. These machines operate with that level of accuracy every single moment of every single day. The first transformation happens inside a machine called a metal-organic chemical vapor deposition reactor. It is essentially a high-tech oven. Gases containing gallium, nitrogen, and other elements flow into a sealed chamber where they decompose and reassemble, atom by atom, onto the sapphire wafer surface. Layer after layer of gallium nitride crystal grows in the darkness of that chamber. This is the birth of the LED, not assembled, not printed, grown, like a crystal forming in a cave, except this cave costs $15 billion to build, and the crystal is engineered to emit light in exact wavelengths of red, green, and blue. When the wafer emerges, it has changed. What was once a plain sapphire disc now shimmers with iridescent color, like an oil slick on water. Those colors are not paint, they are physics. The thin gallium nitride films bend and reflect light differently, depending on their thickness, and that thickness has been controlled to within a few atoms. This single wafer now contains the raw material for millions of individual micro-LED chips, each one smaller than the period at the end of this sentence. But those chips are still trapped in the wafer. They need to be defined, separated, and tested, and that requires photolithography, the same technology used to make computer processors. Ultraviolet light is projected through a mask onto the wafer surface, which has been coated with a light-sensitive chemical. Wherever the UV light hits, the chemical hardens. Wherever it does not, the chemical washes away. What remains is a microscopic blueprint, a pattern of millions of identical LED structures etched into the wafer with surgical precision. Then comes the etching, where chemical baths and plasma reactors carve away the unwanted material, leaving behind perfectly formed micro-LED chips standing like tiny skyscrapers on the sapphire landscape. Every single one of those chips must work. Every one. On a display this size, even a handful of dead pixels would be visible and unacceptable on a product that costs more than most cars. So each chip is tested while still on the wafer. Microscopic probe needles descend onto the surface and send current through each LED. One by one, they light up. Red, green, blue. Millions of tiny points of light flickering on and off in rapid succession. A quality control ballet performed at the speed of electricity. Now comes the moment that defines micro-LED technology and separates it from everything else, the mass transfer. This is the step that took engineers over a decade to perfect, the step that consumed billions in research, the step that makes this entire factory possible. The challenge sounds simple. Take millions of micro-LED chips, each one roughly 100 micrometers across, and move them from the sapphire wafer onto a glass backplane with pixel-perfect accuracy. Simple to describe, nightmarishly difficult to execute. The solution is an elastomeric stamp, a soft, precisely microstructured pad that presses against the wafer and picks up thousands of chips simultaneously, like a rubber stamp lifting ink from a pad. But instead of ink, it lifts microscopic semiconductors. The stamp then moves to the glass backplane, a sheet of glass over 2.5 meters across that already contains millions of thin-film transistor circuits, each one designed to control a single micro-LED. The stamp presses down, the chips release, and in that single press, thousands of LEDs find their permanent home. This process repeats dozens of times, tiling the entire glass surface with red, green, and blue subpixels until 24 million individual light sources are in place. But perfection is not achieved in a single pass. Automated cameras scan every square centimeter of the populated panel, searching for chips that landed crooked, chips that are missing, chips that are damaged. And when defects are found, a laser repair station takes over. A micromanipulator, guided by machine vision, picks up individual replacement chips and places them into position with sub-micrometer accuracy, 1 pixel at a time, 1 repair at a time, until the panel is flawless. The populated panel then enters a bonding furnace, where heat and pressure permanently fuse every micro-LED chip to its corresponding circuit on the glass. 24 million simultaneous solder joints, all formed in a single thermal cycle. When the panel emerges, those chips are no longer sitting on the glass. They are part of the glass, a permanent, irreversible union of semiconductor and substrate. A protective encapsulation layer is applied next, a transparent barrier that seals the micro-LEDs away from moisture and oxygen, the two enemies that would slowly degrade them over time. Ultraviolet curing lamps harden this barrier in seconds, locking the LEDs behind an invisible shield designed to last decades. And then, the moment of truth. Power flows into the panel for the first time. First, scattered points of light appear like stars emerging at dusk. Then entire sections ignite, and within seconds, the full 120-inch surface is alive, radiating pure white light with a uniformity and brightness that no other display technology can match. This is MicroLED, no backlight, no color filters, no liquid crystals. Each pixel produces its own light, its own color, independently. The result is perfect black because a pixel that is off emits zero light, and perfect brightness because there is nothing between the LED and your eye. But raw performance is not enough. Every panel must be calibrated. In a darkened room, spectroradiometers measure the luminance and color of hundreds of points across the screen. The display cycles through red, green, blue, gray ramps and white fields, while software adjusts the driving current of individual pixels to achieve absolute uniformity. This is not a television that is good enough. This is a television where every pixel on a 10-foot screen matches every other pixel to within 1%. Dead pixel inspection follows. Machine vision cameras scan the entire surface at high resolution, searching for any pixel that fails to illuminate or displays the wrong color. On a screen this expensive, zero defects is not a goal, it is a requirement. The completed panel then enters burn-in testing, running continuous dynamic patterns for hours to stress the electronics and verify long-term reliability. If a pixel is going to fail, it will fail here, in the factory, not in a collector's living room. After burn-in, the panel cools in a climate-controlled staging area before assembly begins. The thermal management system, a large aluminum heat spreader with precisely placed thermal interface pads, is mounted to the panel's rear surface. A brushed aluminum frame is assembled around the perimeter, providing structural rigidity to what is essentially a very large, very thin, very fragile sheet of glass. Robotic torque drivers insert screws at exact specifications around the frame edge, each one calibrated to avoid stress fractures in the glass. The framed panel is then mounted into the television chassis, a precision-engineered enclosure that houses the power supply, the main processing board, Wi-Fi antennas, and all the cabling that connects brain to body. A technician routes ribbon cables through molded channels, plugs multi-pin connectors into headers, secures wire bundles with ties at measured intervals. It is not just assembly, it is architecture. Every cable has a path. Every connector has a purpose. Every component has been placed to optimize signal integrity and thermal performance. The rear housing seals the electronics away. A multi-spindle screwdriver drives all perimeter screws simultaneously, a mechanical symphony of synchronized torque. And just like that, the television is whole. Final calibration happens in a dedicated darkroom. Final visual inspection is performed by a senior technician who walks the length of the screen with a flashlight, checking for micro-scratches, surface anomalies, and cosmetic imperfections invisible to anyone but a trained eye. This is the human judgment that no machine can replace, the final authority that decides whether this particular television meets the standard. When it passes, the screen powers down for the last time inside the factory. The surface goes black, becoming a perfect mirror that reflects the clean room where it was born. There is something almost ceremonial about it. Packaging is its own engineering discipline. A custom wooden crate lined with precision-cut high-density foam receives the television vertically, supported at every edge and corner. Desiccant packets control humidity. Shock indicators will reveal if the crate is dropped. Steel bands and stretch wrap secure the container for global shipping. A climate-controlled truck awaits at the loading dock, its interior maintaining the same temperature and humidity that protected the television throughout its entire creation. The doors close. The truck departs,